Very good. Let me get a new color, maybe today gray. Okay. So interaction Hamiltonian engineering, we need to start thinking about what's going on. So to overview this guide, it's you think of individual qubits, one moment to think what kind of qubit is this one. There's one Josephson junction, so it looks quite basic. You'd conclude, okay, a regular transmon, yeah? So why just regular transmon? Because that's the earliest thing, and maybe you have also some outside, maybe you have some outside references, so maybe it will be easier to deepen your study if you're actually studying the coupling of two qubits. So what's going on with the capacitive coupling? It's basically saying that you have two qubits and there's some capacitor between them, which is something you can fairly easily engineer using all this kind of etching and whatever you use for the fabrication of the hardware. Okay, so basically to couple two qubits in this way, you will have this capacitor here. What's the problem of this? This is something that we would probably call an always-on interaction. Why is it always on? Because this capacitance here doesn't change at all, okay? But it's interesting what happens when we couple those two things. And what you will see is that you can derive a coupling Hamiltonian, which will depend on the C parameters here of the oscillation frequencies here, omega. And this G112 will be coming from the modeling that we have that will give us the strength of the coupling of those qubits. Okay, so that's an always on coupling. So now we can ask what happens if we do something like this but mediated by a resonator. So it's called capacitive coupling, capacitive here, coupling to of the two qubits. That's the two qubits. Why? Because we have the Josephson junction here. The Josephson junction here carries this inductance, okay, as a parameter. So if that wasn't clear in the, I want to erase. Okay, if that wasn't clear in my recap, then again, that's how you recognize the Josephson junction here. Why is this interesting? It's interesting because maybe I can tune the frequency of that oscillator. Maybe there's a way to tune that frequency of that oscillator. And if that would be happening, then maybe I can time dependently, for example, do some coupling of the qubits. Yeah. So for example, if those frequencies here, omega, are like this, and if I have this frequency here, maybe they get more strongly coupled, but then maybe if they are on resonance, maybe there's a stronger coupling, and so on. Yeah, those kind of ideas. Then you keep reading and you can verify what's going on. That's more or less the ideas. So if we get until here, we are more or less happy. The inductive coupling is similar. I mean, basically the idea is that somehow the flux from here will jump over to here, mediated by some electromagnetic transition here. Okay, so I think maybe not so crucial to discuss the inductive stuff in a big detail. Okay, so our structure is what happens if there's a capacitor coupling two qubits, and what happens is to probably this section here. So let's see. A capacitor is placed between the voltage nodes on the participating circuits, yielding an interaction Hamiltonian of the form this. Okay, so basically the voltage operators, you can think of them as being some quantum operators. Why are they quantum operators? It is because there's a quantum fluid which is carrying the charges, and then the density of the charges are more or less quantum. So if there's more of them moving around, the potential is kind of quantized as well. Okay, so that's what's going on. in the end, this is all blah, blah, what I said, because, you know, you can skip through and go to the really interesting Hamiltonian, which actually is a derivation. I see it already because of this kind of limit here. In the limit of that, we get this Hamiltonian. So more or less, you can forget everything that was confusing before. And unless you will be working exactly on designing that stuff, you continue with this Hamiltonian, trusting other people who wrote a paper about this being the right Hamiltonian, for example. So what do we have here? We have a summation, which is basically our two qubits. Those two qubits are exchanging the excitation in this nonlinear harmonic oscillator way. Okay. Why is this possible? Is because there's some sort of loop, which is kind of the transmon qubit. So that's how it arises there physically. And now those two qubits, this is their energy of the individual qubits, but this is their coupling energy, okay? And the way you kind of derive this kind of stuff is that the voltage parameter will be proportional to this kind of charge number operator, okay? So the charge interaction, this kind of interaction potential is okay. Then there is a calculation which I find a little bit strenuous, because you need to operate on matrices of capacitances and so on. But in the end, you can get the nice result. So it's actually more pleasant to look at this. Okay. SQ circuit can give you those Hamiltonians automatically. That's the point of that package. It's quite nice. And then you can try to see whether you will get a similar Hamiltonian, and you can study it in more detail. Okay. So now this gives us a form of the interaction. And then later, when we say that the unharmonicity is so good that we have only two levels, then basically A dagger A becomes our sigma Z operator. And this will have a form in terms of the Pauli operators in those assumptions. So as we will be going down the review later, we will be searching for something like this, that basically we will have maybe here omega sigma Z I, and here there will be some interaction. So it might be sigma plus sigma minus and so on. Yeah. Then there's a lot of discussion about what are those effective models in this kind of qubit land of transforming this. Okay. So there's a few levels of taking the approximations. Okay, but this Hamiltonian is really relevant, and it's actually quite pleasant. So what it tells us, there's the individual energies of the qubits, and if this charge number operator is kind of doing something for those qubits, then they are interacting. There's some, let's say, repulsion or attraction of the levels. Okay, good. One thing to note is that this is derived under the approximation CG smaller than the capacitances of the qubits. What this means is that this will be something that will continue when you are studying the operations on the qubits, which means that this coupling here might be a fairly small number, because the CG smaller than C1G. So if you want to have this large coupling, then they shouldn't be too small. Yeah. So that's one word of caution. So what kind of coupling do we get? I just wanted to highlight the CG is really the capacitance of the coupler. Okay, so this G is often the interaction parameter. Okay. So do we need something more? Maybe look at this equation, that this is relating V to the interactions, and then it's just like arithmetics. Okay, so yeah, then just reading through and everything will be fine. If we have a magnetic inductive coupling, then this inductive coupling is not in terms of n, but it's in terms of phi. Okay, so I won't say more to this because yeah, we just read through and everything is well. In the end, it's becoming a little bit more technically detailed, but it's a similar structure of the Hamiltonian. I guess there is some stuff to say about this, but I'm not so particularly familiar with that. And if I will ever need it, I will read more about this inductive coupling. For now, I didn't need it, so I won't say much more there. So when we have n, we have basically this unharmonical mode in each qubit, which has its creation annihilation operators ai, where I is the index of the qubit. And here we are doing this Duffing Hamiltonian approximation, which means you retain the quartic term, you have the harmonic oscillation term, and then you need to express the coupling between the qubits as this kind of operation here. Yeah, this is not exactly n, but basically. Basically, this is more or less like position momentum operators. Okay, if I look at something like this and something like this is the position momentum transformation of regular harmonic oscillators. So if my potential or current is proportional to that, then that's one way to think about this. I'm not really trying to connect everything together here. You can ask yourself how this Hamiltonian connects to the earlier stuff. For now, that has a link between the previous Hamiltonian and this one. What is more important for us is this arrow here that I will erase and draw again. Those are scribbles from last week with the outlook. Okay, so from this Hamiltonian, we come to this one, and this is super cool because we have a fairly simple Hamiltonian. You see that this has a local artificial magnetic field, yeah? So basically you have an effective new model. And because of this, there's a coupling, and we would say that there's a coupling in sigma y. So it's a non-diagonal Hamiltonian, okay? And now if we were able to tune the G parameter, then we would be able to, let's say, tune when the interaction appears and when it doesn't. If it's always on, then maybe that's limited, and you would do something else to control the qubits. Okay, and the review, of course, describes those ideas and so on. Yeah, should I say more? I don't know if I want to say more. So basically, the structure here was that you go to the second quantization, and yeah, maybe I should still talk about this. So even though this has an interpretation of maybe some charge number, we have the commutation relation of n and flux, which is bosonic. Okay, and because of that, we can associate with them momentum relations, and from those momentum relations, you can construct creation annihilation operators. That's a little bit abstract, but that's kind of how this kind of worlds of quantized currents is working. So because of this, something that normally would be second order is first order for this. Yeah, and more or less what it tells you is that the quantized potential and current, they are not commuting. This is similar as in quantum optics, that the electric field and magnetic field, they also don't commute. Okay, so that's a similar thing, and that's a feature of those quantized currents. So we get that, and that's more or less where this paragraph nicely will explain to you how to go from those kind of Hamiltonians to those kind of Hamiltonians, which are much more standardized. Yeah, because we start forgetting the hardware parameters. We are starting to having more universal qubit Hamiltonians. So now omega, as we said, depends on the charging energies of those Josephson junctions. But once they are fixed by having a fixed hardware realization, there will be a frequency of the qubit. So you forget after you realize the qubit with the fabrication, you forget that kind of stuff. There will be maybe some harmonicity operation that comes from maybe those parameters of the Josephson junction, but then they are also fixed. And once you fixed your capacitance, you have also your coupling G between the qubits. Okay, and that's kind of what you need to take from the reading, plus the technicalities, which are of course worth to know. But once we are comfortable to be working with that, we can kind of forget those hardware things. Yeah, because now you can start talking about making a two-level approximation to say that the higher order level gets never occupied, and then basically, yeah, basically we get a two-level approximation. So if you ignore all higher level operations, one thing that is important is that there's a transverse coupling, and the coupling is transverse because it doesn't have diagonal matrix elements, but it's switching the excitation levels of each qubit. Okay, so that's called transverse. So we need to remember that transverse means flipping qubit occupation numbers. Okay, this you find in this paragraph here. So now we have a qubit Hamiltonian. Great, that's the first qubit Hamiltonian that we got. So after a lot of talking about superconductors, about capacitances, maybe some splitting to get a Josephson junction, just some tunneling on the Josephson junction, creating loops of that, considering the quantization, you get Hamiltonian 32, which is kind of the achievement, 32 equations to get to the first qubit Hamiltonian, which is kind of two independent qubits with a small coupling between them. Okay, so if you continue reading, you can study it further. Yeah, there will be some discussions, and you will see that it's worthwhile to consider maybe some approximations to see that there's other considerations that we can do. So transverse coupling can be engineered between a qubit and a harmonic oscillator, as in figure 3b. So do I have the figure 3b? Let's see. Figure 3b. So basically the Hamiltonian that we will be looking at will be something like this, where this goes, it's cut off, so that this qubit doesn't couple to it. So, and if this is a quantum resonator at a frequency range of this qubit, okay, this frequency range of this qubit is defined as the two-level transition between the qubits. I see some question maybe in chat. Yeah, so there was a comment that there's a rotating wave approximation happening. Actually, what I was trying to describe is that this is not a rotating wave approximation, but more related maybe to bosonization or something like this. Okay, rotating wave approximation will come later. And rotating wave approximation, where we will see it later, I think somewhere later. I don't know, it will be there. Rotating wave approximation is expected to play a role, and it's a good question whether rotating wave approximation was used. I think in this case, maybe not, because the excitation is just swapping from the qubit to the oscillator here. Yeah, so maybe it wasn't used. What this model is assuming is that the qubit is fully anharmonic, so only two levels, but the harmonic oscillator doesn't have a nonlinearity, so it's fully harmonic. Okay, And then this transition here of the artificial spin and the kind of photon is actually an exchange of the same medium, so to speak. It's just that other loop, which is the transmon, is forced by the Josephson junction to suppress those higher levels, but it's a similar medium in the end, yeah. So there's nothing crazy going on. So in the end, the underlying hardware is a medium that can talk to this other medium. And you get this Hamiltonian here, okay? It's again several lectures to talk exactly about why those Hamiltonians are there, but I'd argue that you don't need to know much more than to say I have a qubit, I have an oscillator, and those two can exchange their excitation. So I can lower the state of the qubit. So which one? This one lowers the state of the qubit, but puts that energy somewhere into the oscillator. Or you take out stuff from the oscillator and flip the qubit, okay? And that's often enough to understand, okay? So what's going on is that maybe what I could do is I could try to use an FPGA to put some energy into a cavity. And once I will put the energy into the cavity, I will start increasing the occupation numbers of that cavity. And then my interaction will take my excitation that I added to my cavity, which is my harmonic oscillator. And the interaction will change the qubit. Actually, what will happen, so you can see that I did it wrong. I will remove from the excited cavity or oscillator from outside. I will remove the excitation, but I will excite the qubit, okay? So will we see that this is called the transverse coupling to a cavity or something like this? I think this will be, I think we saw it somewhere. Maybe it would be worth to discuss more, but transverse coupling can be engineered between a qubit and a harmonic oscillator. Okay, so that's what we get. So now you see that I was able to maybe argue that this will become a little bit more more controllable, but it's not really allowing me to fully control the whole thing yet. And yeah. So that will be a longer story. I guess then you just continue reading. That will be more or less what this text will be describing, that this is more or less the goal, to be able to understand how to control and move around the qubits. Okay, so what's going on here? Cavity or resonator to mediate coupling between two qubits. So let's see how this is done. Now the Hamiltonian is a little bit more sophisticated. That's the unharmonicity of each of the transmons. I is equal 1 to 2. Okay, that's fine. Then there's the cavity, which is sitting in between. That's my resonator with some frequency omega resonator, coupled here by some capacitor and another qubit. So this one has omega 2, this one has omega 1. Right? So what's going on through this capacitive coupling, as we understood in equation, I guess, 33, we just repeat that stuff, but with some sub-indices. So now the resonator has a sub-index because we went away from the two-level approximation and allowed for this unharmonicity. We get creation annihilation operators and not sigma operators. Okay, so that's what's going on here. So we kind of see that the equation is corresponding to this nasty picture that I erased, because you have figure number 3b to tell you exactly how this looks. Yeah, fine. We don't need the figure. We can read it off from this, and we see that this is basically two components of the same thing, which was the previous equation. When you read it, you might get lost, but remember this kind of modularity, because that's the whole spirit of superconducting qubits, that this is fairly modular. Okay, so two inductively coupled qubits, that's maybe relevant for some cases, but yeah, okay, let's discuss this. We have this term longitudinal coupling because this commutes with that. Wonderful. Okay, so that's the difference. Yeah, there is something about the qubit frames. When you will read it, you will probably be able to follow, and I'm not even trying to explain this because if you want to follow it properly, you need to invest some time into it. So just know that you need to be more deliberate to follow those details there. And then I think you can just continue reading and we'll be fine. Okay, there can be mixed type interactions. Great, we kind of understand what's going on here. So basically, this is changing the state of the oscillator, but this is changing, so to speak, the frequency of the qubit. Okay, so if I would have my cavity in a coherent state, then this would be more like a P operator or something. So that's maybe not moving the cavity too much, and then basically the cavity is doing something to the frequency of the qubit. So you could say that, okay, it's not exactly that, but you could say that there is a frequency. If I would put expectation values here, there's a cavity dependent frequency. Okay, so basically dynamically the cavity can move the frequency of the qubit. Okay, that's actually a cool effect and would be relevant. Okay, so we discussed this kind of yeah, coupling of qubits, longitudinal coupling, transversal coupling. Yeah, that's those sections. That's more or less what comes to my mind when I'm just looking at the overview of the equations. There's maybe some question. Okay, so again, what does transversal and longitudinal mean? Okay, let's look at that. So this part, this section here explains longitudinal, basically meaning that there is some diagonal occupation numbers of the coupling element, okay, coupling terms. A little bit easier to understand for the transverse part. So let's look at this, and then you can zoom in yourself on the other stuff. So our potential is part of our, whoop, that wasn't very smart. Our first coupling element was voltage to voltage coupling, okay? Then we look further in second quantization, it will turn out that voltage is proportional to this P or Q transformation of annihilation, creation or annihilation operators, okay? So what are expectation values of those voltage operators? If I look in the occupation basis of the modes, then I see that there's zero expectation value of this VI operator, okay? But there's a non-trivial expectation value that is switching the occupation number of the qubit, yeah? The level of the qubit gets switched. And that's something they call transversal, okay? So depending on the hardware, so the physical character of the coupling, which is either capacitive or inductive, is modeled by certain quantum operators. Those quantum operators that get involved in those effective coupling Hamiltonians, they have certain characteristics in terms of matrix elements. And if it turns out that they are diagonal in this kind of qubit basis, then there must be some off-diagonal coupling, otherwise it's a zero matrix, yeah? And so if you get this transition, of the qubit state, you call it transverse. Yeah, that's the transverse coupling. And then we explain, if you do it inductively, in italics we said longitudinal, then it's great. And then the last paragraph, the kind of finish where we don't have much energy anymore. It says mixed qubit interactions. Okay. In addition to pure transversal and pure longitudinal, we can have examples of mixed interactions, reference 100H, for example, that we'll be discussing it probably. Yeah. Good.